Today I'm going to talk about a classic problem called cardinality estimation, but from an information theoretic point of view. So let 1 to U be the space of all elements, and let A be a sequence from that. And we want to know the number of distinct elements in A with just one pass of the sequence. So basically we're in a streaming setting. So the trivial algorithm will be the check and count, where you just do the exact counting. The good point is that the counting is exact, but it takes too much spaces. Especially in practice, usually a decent estimation is enough. We do not need to know like the exact cardinality. So the question is, can we do better in terms of the memory if we just want a decent estimation? The answer is yes. So the basic technique is sketching. For example, the PCSA sketch hashes all the elements abstractly to a point between 0 and 1. It divides geometrically the interval into cells and store bits for each cell to indicate whether there is a point in it or not. So like this is a possible execution. So in practice, it suffices to store, roughly speaking, log U bits. So you only need to store like the bits for the first log U cells. And hyperlog sketch like basically has the same setup, but instead of storing bits for each cell, it just stores the position of the high cell that contains any point. So maybe a more natural idea is just the min sketch, where it just stores the minimum hash value. And I want to mention 2 points. First, like for PCSA hyperlog log, here we use basically a base 2. So we use 1/2 and 1/4, 1/8 as the ticks, but in general, this can be easily extended to a base Q PCSA. We call Q PCSA and Q hyperlog log. And second, note that all the 3 sketches here are only sensitive to the cardinality of the sequence. So, I mean, they are insensitive to the permutation and insensitive to the duplicates of elements. So, for the study of this topic, there are 2 models that people assume, 2 different models. The first is what we call the standard model, where you have to store the hash functions explicitly. And people there use epsilon delta approximate to measure the performance of the estimator. So if you assume U is a constant, let's say 2 to the 64, then the lower bound and upper bound matches in this model asymptotically. Our work assumes another model called random oracle model. So in random oracle model, we assume free access to truly random hash functions. And usually we require like the estimator has to be unbiased in this model. And given that it's unbiased, then we can use like variance to measure the performance of an estimator. Specifically, we use the notion of asymptotic relative variance. So consider when the cardinality is large. So let M be the number of independent subsketches used. So like in the previous example, each strip is just 1 subsketch. To reduce the standard error, you can increase the number of sketches you use. And this table contains what's the like estimation error we have for the examples we have before. I have to note that so the hyperlog log use the same sketch as log log. The difference in the standard error is just an improvement in the estimator solely. So in this model, people usually do their papers like first propose an algorithm and then do the analysis. There is like, for example, naturally I want to know what's optimal. What is optimal? Like in terms of the memory variance trade-off. Of course, you can always you must look at the memory variance trade-off because you can always reduce the variance by increase your memory, or like reduce the memory usage by the cost of your variance increase. It turns out that we need to look at the memory variance product as a quantification of the memory variance trade-off. So if you take the table and take the product between the sketch size and the variance, this is what you get. It is a constant depending on U, but does not depend on M. But this is not enough because I don't want this measure of memory variance trade-off to depend on the way you store the sketch and the way you do the estimate. So in fact, we should assume the smallest possible memory variance product that a sketch can achieve as its performance measure. Specifically, we should assume optimal compression and optimal estimation. Then we are going to see how can we characterize like optimal compression and optimal estimation by two important information numbers. So let's start with optimal memory size. The trick is to fix a specific cardinality lambda. Once the lambda is fixed, the outcome of a single sketch is just you can consider it as a random state, random variable, like a random state. And you observe m of them, m independent copies of random states. So in order to store the outcome of the state given lambda, you need at least m times the entropy of the random state. Let h lambda be the entropy of the random state given lambda of a single sketch. So then this is achievable by some perfect compression method, like arithmetic encoding. So we should use m times the Shannon's entropy as a memory size of a sketch. The second, let's see what's the optimal estimation. First, the trick is again to fix lambda, and the problem is in fact a standard point estimation problem, like in statistics. So you have a distribution family parameterized by your cardinality. With your fixed and cardinality, this distribution family gives a distribution, like which is the distribution of the final state of a single sketch. And fixing a unknown lambda, so we observe m independent observations, which is just the memory state. And we want to guess what the cardinality is, basically what the parameter is. So this is just exactly the point estimation problem. So we can use the results from the point estimation. So it turns out that the variance of any unbiased estimator is lower bounded by 1 over m times the feature information number of that distribution family, where like the feature information number might be less familiar to us, like comparing to the Shannon's entropy, but it basically quantifies the amount of information revealed by the observations about the hidden parameter. What's more, it's asymptotically achievable. In fact, under mild conditions, the maximum likelihood estimator achieves the Kramer-Ross bound. So, a side note is that because we care about relative variance, so here, instead of 1 over m times the information, we have 1 over m times lambda squared times the information. And we call lambda squared times the information as the normalized information. And we should use this normalized information to characterize our optimal estimation error. So what we have now? So let m be large and we fix a certain lambda. So the minimum number of bits needs is m times the entropy, and the minimum relative variance needs is at least 1 over m times the normalized information. So the memory variance product we can achieve is the entropy over the normalized information, which is nice. But we are not done yet, because this memory variance product still depends on the lambda, depends on your hidden parameter, which is not ideal. As an analogy, let's say we are designing some rulers, which is used to measure the length of objects. We don't want the ticks on the rulers to be uneven. Basically, we want to have the same precision for objects of different lengths. So, in practice, like ideally, we want a ruler with fully even ticks, but this is kind of too much. But it turns out that we can start with a notion of weak scale invariance, where most previous the sketches I mentioned before, both PCSA and hyperlog satisfies. So we say a sketch is weakly scale invariant in base Q if both their entropy and normalized information is multiplicatively periodic in Q. And especially in such cases, their memory variance product is also multiplicatively periodic in Q. So now, assuming this, what we have, like as an analogy of the rulers, is a ruler with not fully even ticks, but with the distribution of the ticks is periodic, which is better than an arbitrary set of ticks. So to demonstrate like the phenomena of the small oscillations of the performance of, because I've stated that the hyperlog and PCSA are in fact not fully scale invariant, but just weak scale invariant. Let's see some experiment. Here I just plot the estimator over the true cardinality over a range of cardinality, and plot the points where each point corresponds to one experiment. You see the oscillation is insignificant. We don't spot any significant oscillation there when Q equals 2, for the hyperlog. But as I said, you can increase the base, and once say we increase the base to 16, the performance oscillation becomes significant. There are some positions where your counter have a large variance, and there are some positions your counter have a small variance, and the oscillation has period of exact 16. But it's kind of easy to smoothing that. Then the idea is just using random offsetting, and for each subsketch, while initializing, you sample uniform random variable from 0 to 1, and you just accept only q to the minus ri fraction of the incoming elements for each subsketch. So as the analogy for rulers, so why this can smoothing things out. So basically we are trying to measure like the length of objects using multiple rulers, but instead of just measure it multiple times, each time we measure it, we just pre-offset it. And so if you see the green object, this ruler gives a large variance, medium variance, small variance. And if you look at the gray object, this gives a medium variance, large variance, small variance. So with the random offsetting, no matter what the length of the object is, an average is always gets an average variance. So you can see experimentally, after applying the random offsetting, the performance oscillation of the hyperlog of base 16 is smooth. So now finally we can come to the definition of Fish number. So for weakly scale invariant sketch with random offsetting, no matter what your cardinality is, the Fisher information and the entropy is always the average Fisher information and the entropy. So we can define the memory variance product as we showed before. So the entropy over the normalized information, which is m times the average entropy of a single sketch over m times the average normalized information. M cancels out, and the average is just the integral from 0 to 1 over q to the r. So note that what does it mean? Fish number is just a measure of a sketch itself, which does not depend on how you implement it. How you store the sketch and what estimator you use based on the sketch. So it means it's a tight lower bound on the memory variance product of all implementations of C. So now we can head on to compare, for example, hyperlog and PCSA using this Fish number measurement. So before that, let's try to formally define QPCSA. So we care about the case where lambda is large, and say lambda is large, lambda uniformly random points in 0 and 1 can be replaced by a Poisson lambda process. And so in general, it's for general natural base Q generalization, PCSA, it basically stores some bits, and each bit corresponds to 1 cell of size Q to the minus I. And the underlying that is a Poisson lambda process. So due to the memory list of Poisson point process, given the fixed cardinality lambda, what you observe is in fact a sequence of coins where each coin has bias e to the minus lambda times q to the I minus I. And let's quickly see why QPCSA is weakly scale invariant. Because if you consider the case the cardinality is q times lambda, you basically, the distribution of your observation is just a shifted version of the distribution when the cardinality is lambda. So they have the same entropy and the same normalized information. Okay, before do the calculation, let's just look at single cell, which is an important building block. So let's consider a cell with heating probability P, which corresponds to a coin with bias e to the minus P times lambda. It turns out that the entropy of the single cell and the normalized information provided by the single cell can be written as a functions of P times lambda. So basically, you can consider P times lambda as a local time of the cell, which tells about how sensitive this cell is to the cardinality. So when P times lambda is small, there's very little chance that the cell gets on. So it's not very sensitive. And when lambda is large, with high probability, P times lambda, like the cell P of size P, will get a 1. So there's not much entropy there, and it's also not very sensitive to lambda. So the cell will have a lot of entropy, but at the same time, a lot of information about lambda when P lambda is about a constant. Now we can just insert what we have into the definition. So the entropy of the sketch is just the sum of the entropy of each independent cells, and the normalized information of the whole sketch is also just the sum of the normalized information of each cell. And by inserting into the definitions, what we have, the Q gets cancelled out. What we have is just H0 over I0, where they can both be analytically expressed. Especially the I0 here is just the sum of the inverse of squares, pi squared over 6. It's a little bit surprising because it turns out that the performance of the sketches does not depend on Q for PCSA. It's always H0 over I0. Similarly, we can do the same calculation for hyperlog log. And it turns out that for all base, that the Fish number of Q hyperlog log is greater than the Fish number of PCSA. But in the same time, if you increase Q to the infinity, then the Fish number of the Q generalized hyperlog log will tend to H0 over I0. So in terms of the Fish number, PCSA is in fact better than hyperlog log. So what we have shown before is just fix the cardinality, and the memory is also talking in average sense. It would be nice to know whether it's possible to maintain this abstract infinite memory within a fixed chunk of memory, within a fixed chunk of bits. So it turns out that yes, we can with just an overhead of log u squared. The next natural question will be, what is the optimal Fish number among the class of weakly scale invariant species? Well, our guess is that H0 over I0 is the optimal Fish number, and we do have some evidence. It turns out that, so for linearizable sketches, H0 over I0 is the optimal Fish number. Linearizable sketches we will define very soon. It's a pretty natural class of sketches which contains most sketches in history. So let's first look at a general model to describe cardinality sketches, the dartboard model, where you start with a board and you divide it into cells, and you can consider the insertion of elements as throwing darts to the board. So there are 3 rules. So first, if a free cell gets hit, that cell gets occupied. But in the meantime, this hit may cause other free cells to be occupied as well. And the rule 2 is, if a dart hits an already occupied cell, then nothing changes. And the third is once the cell is occupied, it never becomes free. So in this model, a sketch is called linearizable is, let's say, Zi is the indicator whether a cell is hit or not, and Y is the indicator whether a cell is occupied or not. And we say a sketch is linearizable if you can permute the cell in a certain order where whether a cell is occupied or not only depends on, first, whether it's been hit or not, and second, whether the precedence of it has been hit or not. Clearly, PCC is linearizable because you can just write phi equals 0. Like each cell, whether it's occupied or not, only depends on itself. And Havelock log is also linearizable because every cell, like whether it's occupied or not, only depends on like the cell before it and depends on all of it. So I'm not going to present the whole proof of this, but I'm going to give some intuition, and the intuition is pretty neat. Like the proof of this is like a dual version, a dual of the calculation of the Fish number of PCSA, where in that calculation we consider a specific moment, lambda, a specific cardinality, and with the entropy and information of all cells of different sized cells. But here we consider a single cell, but its performance over all the cardinalities, which we call the lifetime. So recall that we call the time of a single cell as p times lambda. So let's consider, what's its contribution and occupation like in his lifetime for a linearizable sketch. So if it is forced to be occupied by its precedent, then it just contributes zero entropy and zero normalized information, because it just doesn't matter whether it has been hit or not. Otherwise, if it's not being forced to be occupied, then it's just the same as a free cell of size p, and it just contributes entropy h p lambda, while provides normalized information I of p lambda. So if you plot that out, you can consider, let's consider a free cell. So when p times lambda is a constant, there is some decent information you can extract it, but it also takes a decent amount of entropy to store. And when p times lambda is large, both get small, and when p times lambda is small, both also get small. So what we should consider is in fact the economy, the ratio h over I. And it turns out that this is monotonically decreasing, which means a cell just gets more economic in terms of this entropy and normalized information trade-off as time goes on. So basically, you should never kill a cell. And this is, roughly speaking, the proof of why PCSA is optimal among the class of linearizable sketch. So as a conclusion, we emphasize again that we come up with a measurement for sketches, which depends on two celebrated information notion. One is Shannon's entropy, and one is normalized phase information. And in fact, this kind of ratio between Shannon's entropy and phase information should in general appear a lot in the streaming setting, because we want to estimate something. We want to know the information of a hidden parameter. But at the same time, we have to store the observations we have. So there's always a ratio between entropy and phase information there. So some open problem will be, naturally, first, what is the real optimal phase number among the class of all weakly scale invariant sketches, instead of just within the class of linearizable sketches? And the second is, so like we said, we didn't care too much about runtime before, but if we do care about runtime, can we design some simple sketches where you just perform a very specific way to compress and to estimate whose memory variance product approaches H0 over I0? That's it. This is the reference. Thank you for listening.